Okay. Uh, Good morning to all. So, welcome to day two, lecture three of this Gyan course on microfabrication technique and device integration, principle, process, and application. Today's topic is properties of material for MEMS. So, with this introduction, I welcome the expert to deliver his lecture.
Thank you very much, the chairperson. And today, very good morning. Today, I would like to continue our course on the MEMS, microfabrication and integration. So today's topic will be properties of material for MEMS. As we know that MEMS has a different characteristic where at the small scale it behaves differently. So the selection of materials and the use of materials in MEMS will be crucial in order to make sure that the device will be function accordingly as intended. So we will look into the properties of the materials, and firstly we will go through the definition and example of the materials. Then we will look into the physical properties, optical properties, electrical properties, and some concern in the health. And this part will be properties when we make things small, which means, as we discussed in the previous lecture, that when we make things small, the properties change. And that is part of the things that we will look as well today. And of course, the first part is the criteria of the materials itself. So let's start the key properties for MEMS materials. Basically, there are a number of properties of the materials which need to be considered from the beginning of the process before we start talking about the device itself. So we need to consider that the materials has excellent mechanical stabilities and strength. For example, high Young modulus, fracture toughness, etc. We have to remember that we are designing something which is at the small scale. So the material has to be function later on when it is at the small scale and is robust enough. So that is where we need to think of the mechanical stabilities and strength. Then another properties is wide operating temperature range, meaning that the materials not subjected to expansion, thermal expansion, where it will affect the performance or maybe subject to bending if the materials bend or expand due to thermal or heat. We know that the operating temperature might depend on the application. The operating temperature might go high or low. Then if it's too small and is subject to thermal expansion, then it will kind of maybe perhaps damage the device. So we have to look into the material with a wide operating temperature range. And good electrical properties like semiconductor or insulation. Then this depends on what is the purpose of the material that you want to use. If it's about electrical conductivity, circuit of the device, then we want to have something good in terms of electrical conductivity. If it's for the purpose of insulation, then it has to be good in terms of insulating the material from circuit or electrical short circuit. And also, we would like to look into the semiconductor properties as well. So that's why normally we use silicon dioxide, or materials with metal for the circuit, etc. And we want it to be low cost and ease of processing. So material that, of course, in whatever process or device or product that we try to fabricate or to produce, we want to have a low cost material, because this is the one of the criteria that will make sure that the device is acceptable at the market, for the market, for the price that you're going to sell. And ease of processing, of course, if it's difficult to process, etc., it might jeopardize certain property, or it jeopardize certain function or features, and it will increase cost as well. Then high durability and reliability, including low mechanical hysteresis. So we know that mechanical hysteresis is such as property that when you expand and you don't go back to the original shape. Okay, and good thermal properties, example thermal conductivity and low thermal expansion. So in MEMS, we try to have materials that can disperse heat quite fast, for example, or it can prevent expansion of the material, as I mentioned before. So with regard of the properties that I mentioned before, so now in MEMS, normally we use silicon as the base material or base structure, because silicon has good at the properties that I mentioned before: semiconductivity, mechanical stability, then and integration potential. And of course, if we remember that in the first lecture, we have mentioned about the origin of this MEMS or micro fabrication process was originated from the semiconductor process. Basically, in semiconductor, it's based on the silicon, or for IC design, etc. So that's why the expansion or extension of this process for the structural design, etc., is based on silicon, and it is found that is very compatible and good materials as to be used in the MEMS devices. Then we have a polymer material, which is for the processing of the fabrication of the device itself, as well as the coating, etc. The polymer materials are also good materials with low weight, with this flexibility, and also lower cost. So we look back at the mechanical properties. What is the concern in terms of the use of mechanical properties here is the Young modulus. Higher modulus is desirable for mechanical stability, with silicon having a modulus similar to steel but much lighter. That is the advantage of using silicon. It's a lightweight, but at the same time is as good as metal, as steel, in terms of the Young modulus. And in terms of strength, a material must withstand applied forces without breaking, especially important for device subjected to significant stress. Then we have mechanical stability and hysteresis. Materials should be dimensionally stable and have minimal or no mechanical hysteresis, meaning they are returned to their original shape after deformation. So I've mentioned before, is if the material subjected to stress or subjected to heat, temperature, the expansion or the deformation of the material will have no hysteresis, meaning to say, if you expand it or you deform it, it will go back to the original shape or the original position. So it doesn't go less or beyond the original shape or dimension. So fracture toughness, a critical property for avoiding crack propagation and ensuring device reliability and lifespan. Then we look into thermal properties of the material. Thermal conductivity, important for managing heat in the device. We know that if you have some circuit or you in the environment of operation with heat, then you need to make sure that your device or the heat will be dispersed uh, fast and do not affect the other performance. And coefficient of thermal expansion, a low expansion of a coefficient is crucial to prevent mechanical stress and failure during temperature changes. We know that many materials, especially metals, when you subject to temperature, it will expand. So this expansion basically is not good in terms of, because we know that micro device is very small and the gap or the things for the clearance is very small. So we don't want to have additional stress to the systems, then it will affect the performance as well. So to have a material with a low thermal coefficient is very important. And operating temperature range, materials should maintain performance and stability across wide range of temperature, as the piezoelectric effect, for example, is temperature independent. So to make sure that material is, can operate if it is a low temperature or high temperature, to make sure that everything is, operationable. Then we look into the electrical and electronic properties of the material. So semiconductivity, silicon inherent semiconducting properties allow for the integration of electronic components on the same substrate, which is ideal for signal transduction. So we know that with the use of silicon, you can dope the silicons to make sure that it become conducting or it become non-conducting. So you know that at a certain threshold, you can make it conducting. With the band gap of the materials itself. So you can have the circuit to be designed on this material, etc. So it is not just about material that for the sake of structural, but it's also for the electrical purpose as well. So electrical insulation, some materials like silicon dioxide are used as insulators to protect device and prevent unwanted current leakage. So we know that for silicon dioxide, we can just form the silicon dioxide on the silicon itself. So it's a kind of a process that you just react the silicon surface with oxygen. Then you get a layer of silicon dioxide. So that is where it's very easy in a way, because you don't need additional materials to be insulator. So you just kind of grow silicon dioxide on your silicon materials. So that is to make it into insulator, because for the device itself, you want the device to be have electrical circuit. So of course, the silicon is material with a semiconductor property. Then you have to have a insulator in order to make sure that the circuit does not affect, or short circuit does not happen when you have your metals on top of the silicon, where you have a layer of silicon dioxide. Then piezoresistive and piezoelectric properties, for example, materials that generate or change electrical properties in response to mechanical stress are essential for sensors. So part of the materials for silicon, MEMS is piezoresistive and piezoelectric property. So for the actuation purpose, then you try to integrate the materials into the system so that you can get actuation, or kind of sometimes you say as a motor or things to move the subject. And other important properties, cost and availability. Of course, I've mentioned a little bit on this. Materials like silicon are chosen for their low cost and widely available. And processability, materials should be easily shaped and processed using techniques like etching. Etching is a removal of materials, deposition, and doping to create micro and nanoscale structure. And reliability and durability, materials must be extremely reliable and durable to withstand billions of movement or operation over their lifespan without failure. So biocompatibility for biomedical application. So because now it's not just about MEMS, we have bio-MEMS, for example. So it's when the material in operation subject to bio uh, materials, so how it can perform or how it will affect the performance, etc. So that is why we have to look into biocompatibility as well. So what I've mentioned before, actually part of the properties of these materials, silicon compound, polymers, and metals. So the criteria, as mentioned, let's say you have a robust compatibility, etc. So it doesn't suit just for one materials, but it's in general of the materials required for MEMS. Then these are the common materials that used for MEMS. We have, of course, not limited to this, but some other materials is depend on the requirement of the device itself. You might use different materials as well. So, but that need to be tested accordingly. As for this material, silicon compound is quite common, and generally people will choose among these materials in order to make sure that you have already established properties that is compatible or good for the MEMS device or micro devices. And silicon, most abundant materials. Single crystal silicon, most widely used substrate material for MEMS and microsystem. So mechanically stable, P or N type piezoresistive can be readily integrated with a silicon substrate. So this will make for ideal for transistor and has same young modulus as steel, but is as light as aluminum with a density of about 2.3 gram per cubic centimeter. So that is the property of silicon. And here, this is the interesting part of the silicon as well, P or N type. Normally, we will choose the material or silicon with a P or N according to the needs of the later on. If we need to integrate with something with piezoresistive properties, etc., then we need to choose accordingly. And silicon, we will go in detail later on, but on top of that, we have to be careful as well for the processing, because in silicon we know you have direction, you have a crystal orientation, then how you process it will be defined by the orientation of the crystal structure of the silicon itself. So it has a melting point at 1,400 degrees Celsius. So this high melting point makes silicon dimensionally stable. So we know that if the material is not that high temperature, melting point is quite low, then you know the material normally will subject to some expansion or thermal expansion if it's a low temperature. Then if it's a high temperature melting point, then you know that at the range of, let's say, operating temperature of maybe up to 60 or 80 degrees Celsius or even 150 degrees Celsius, the material still stable, not subject to heat deformation, etc. So that will be the stability in terms of using silicon. Its thermal expansion coefficient is about 8 times smaller than of steel, and it's more than 10 times smaller than of aluminum. So this is a property of silicon that is most desirable. non-mechanical hysteresis. As I mentioned before, for materials for MEMS, we don't want to have material with hysteresis. Extremely flat for coating and additional thin layers. So you can have of course, the processing to make the silicon flat is something else. You need to have uh, polishing, etc., to make it flat, and you know that you can make it in mirror surface, etc. But of course, that will be something desirable due to the nature of MEMS or micro device, that you want to have a very small dimension, which it should be in the tolerance of the desired micro device design. So extremely flat for coating, greater flexibility in design and manufacture. So flexibility meaning you have a different process in order to remove silicon. For example, you can have etching, you can have compatibility with polymers, and you can deposit certain materials on the silicon surface to make it conducting. For example, you can change the property from semiconductor to semi-conducting, or even insulator with a certain doping. For silicon to be used as a substrate material in integrated circuit or IC and MEMS, it has to be in a pure single crystal form. So that's why, at a certain extent, even though the silica, the sand is cheap, but to make it into silicon is become more expensive, a little bit expensive, because you want to control the purity, the single crystal growth of the silicon. So normally silicon will be growing from seed to make it a single crystal, so that it is pure and you can control the properties, because it's a single crystal accordingly. The most commonly used method of producing single crystal silicon is Koroslavsky or CZAC method. So this is the process. As I mentioned, you use silica, quartz plus coal and coke are melted in a crucible. You have this kind of crucible. You make you melt the sand or quartz here, then a seed crystal here with a seed crystal. Then you grow the silicon, this silicon, what you call it, kind of, what you call it, silicon, bar. It's not a bar, it's a rod, silicon rod kind of thing. So with this silicon, you pull it out of this crucible, then you get this silicon in shape, round shaped silicon, a single crystal. So slowly pulls the molten Si up to form a pure silicon ball. The diameters of the ball organolite balls vary from 100 millimeter or 4-inch. This is a kind of previously with a small diameter, then up to 300 millimeter of 12-inch in diameters. So, and this is the chemical reaction happen as SiC, silicon carbide plus silicon dioxide. You get the silicon, pure silicon, and the byproduct are CO and SiO. So basically, the challenge here, just a little bit on the process itself, to get a high diameter or bigger diameter silicon is a challenge process, because it will be very heavy. So for you to pull up is a kind of setup which require a lot of work to have this kind of shape with a large diameter. So it will be very heavy process. Then you want to control the purity as well. To control the purity when you grow silicon is also a difficult process. That's why it's in a controlled environment and it's a very slow process that to produce silicon. So pure silicon balls of a 300 millimeter diameter and 30 feet. This is the length, 30 feet long, can weigh up to 400 kg. So it's a very heavy. These balls are sliced into thin disc wafers using diamond saw. So you slice it into this kind of shape, and standard size of wafer 100 or 4 inch up to 12 inch. But of course, why is it people want to have a bigger dimension? Because the process itself in IC design, we are aware that in IC design it's a batch processing. So let's say this is a small dimension, 4 inch perhaps, and this might be 8 inch. So the 4 inch, one pass process, you can maybe put, let's say, a 10 chip, okay, with a, I mean, because it's a batch processing, meaning you have a few chips designed, then you slice, you take out the chip and package it. But in this bigger size, you can put more number of units, okay, for one go of process. So that will reduce the cost basically. So that is one of the reason that you want to have bigger dimension of wafer in order to have a batch processing more efficiently. Then you can get you can reduce the time for production and reduce the cost as well. So the single crystal silicon. So if you are, I mean, this is not that, I mean, visible, but here you can see that a cutting. So this basically every silicon will have this kind of marking. Actually, it's a marking to show that the orientation of the silicon. So once you see this, you know that the orientation is 100 for this side because silicon has the orientation of its crystal. So single silicon crystal are basically phase cubic center of FCC structure. The crystal structure of a typical FCC crystal is in this I mean diagram in this figure. So you can see that it has arrangement of atom in this way of FCC. So the lattice is very important. I mean for electronic properties. So single crystal silicon, however, has 4 extra atoms in the interior. The situation is like a merge of FCC crystal together as shown here. So you have this kind of orientation of crystal where it shares at the middle. So merged crystal structure. So total atom in a single crystal is 18. So there are 3 principal silicon compound used. I mean, that is about silicon, and next is on the silicon compound. So I have been mentioning about silicon dioxide as well, I mean, before previously. So silicon dioxide is a silicon compound. So silicon is the base or the substrate materials for structural design of the MEMS process or microsystem. But of course, the use of silicon compound is for different purpose, not normally not for structural, but for, let's say, insulator or silicon carbide, of course, for semiconductor properties, etc., and silicon nitride as well. Each has distinct characteristic and unique application. Then you have a polycrystalline silicon as well. Polycrystalline, I mean, as for the names, it's not single crystal, it's with a multiple crystal structure. So it is least expensive material for the silicon dioxide to offer good thermal and electrical insulation. So I keep mentioning about silicon dioxide for electrical insulation. So also use a low-cost material for mask in microfabrication processes such as etching, deposition, and diffusion. So we know that silicon and silicon dioxide holds different properties. So silicon can be etched by I can't remember exactly. For example, if silicon can be etched by hydrochloric, for example, then silicon dioxide is not. So that's why it says here that it can act as a mask. Mask meaning to protect the silicon from being etched or being removed or being attacked by certain chemical. So the use of silicon dioxide can be used as mask as well. And used as sacrificial material in surface micromachining. And above all, it is very easy to produce. I've mentioned before as well that by dry heating of silicon, you have a silicon, then you flow oxygen, and the reaction on the surface of the oxygen of the silicon with oxygen, you can grow basically silicon dioxide by oxide silicon in wet steam. So you have silicon you heat up as well, then with water vapor or steam, you go pass through the silicon in a furnace, for example, then you can get silicon dioxide as well. So these two processes are kind of common process for you to grow silicon dioxide on the silicon surface. And next is silicon carbide, high melting point and resistant to chemical reaction as well. Ideal candidate material for being masked in microfabrication process. It has superior dimensional stability. And now, silicon carbide also have been a new material. It's not new material, but a new kind of direction for the use of silicon carbide. So people are talking about silicon carbide to replace silicon itself in the IC. So that is where the direction of silicon carbide nowadays is a kind of interesting material for IC design. And next is silicon nitride, produced by chemical reaction, as shown here. You can get silicon nitride used as excellent barrier to diffusion to water and ions, and is ultra strong resistant to oxidation, and many etchants make it a superior material for mask in deep etching. So deep etching is a process that you try to uh, bombard ion of gas in order for you to remove a material or to create a structural material, structural form. Then silicon nitride can be used as the mask as well, and also used as high strength electric insulator. So a part of uh, insulation material, I mean for strong resistance to oxidation, is also used for the electric insulator. It's the same material, but with I mean slightly different value in comparison with silicon dioxide. So these are, I mean, the properties of silicon nitride with different process, LPCVD and PECVD process. You can see that you can get deposition. I mean, for this is process parameters. Of course, then this will be the properties that you can obtain with different process of producing silicon nitride. You can get film quality, for example, is much better using LPCVD than some other properties of the silicon nitride. Then next material is polysilicon. It's usually polysilicon, and it it is an exaggeration of pure silicon crystal with randomly orientation deposited on the top of silicon substrate. So you have your silicon substrate, then you have, let's say, random a small polysilicon grain here, okay, with a different crystal structure, I mean orientation. So a few micron on top of the silicon. So these polysilicon usually are highly doped silicon. So you dope with something and you can get a polysilicon. They are deposited to the substrate surface to produce localized resistor and gates for transistor. And being randomly oriented, polysilicon is even stronger than single silicon crystal. So we dope silicon in order to get different properties. We dope with bismuth, for example, to make it more conducting in terms of electrical properties. For example, then we get to be used as different function. And see here, polysilicon properties in comparison with alumina, silica, you have quite reasonable here, young modulus, and coefficient of thermal expansion is very low, is in comparison with alumina, for example. And for polysilicon, you have 160 in comparison with silicon 190, and you have with silicon dioxide with different process. This is in thin films. This is substrate, of course. So with different process for silicon dioxide, you have different property. Then you have polyimide. This is polymer, and aluminum 70 in terms of young modulus. You can see that polysilicon and silicon is much higher in terms of young modulus. Then coefficient of thermal expansion, you can see here polysilicon 2.8, silicon 2.6, and of course you see this is aluminum 25. So as for metal, thermal expansion is very high. Then you can see that silicon and polysilicon are stable materials with regard of thermal expansion. So that is part of the properties that required for MEMS or micro devices, as I mentioned before. And next material is polymers. Polymer in the process of microfabrication is a very important material for the masking and also for protecting or insulation purpose. And polymers include plastic, adhesive, plexiglass, and lucite. And principal application of polymer in MEMS, currently in biomedical application and adhesive bonding. You want to bond the silicon substrate, for example, you use polymer as substrate in electric conductivity made possible by doping. And a molecular structure of polymer is made up a long chain of organic hydrocarbons molecule, and the molecules can be as long as a few hundred nanometer. And characteristic of polymer, low melting point and poor electric conductivity. So meaning to say, if you want to use as insulator, it will be very good. And thermoplastic and thermoset are common industrial product, and thermoplastic are easier to form into shapes, and thermoset have higher mechanical strength even at temperature up to 350. So this will be dependent on the application that we want the device to have. Then we can choose the polymers accordingly. So polymer are popular materials used for many industrial products. For the following advantage is lightweight, ease in processing, low cost of raw materials and process for producing polymers, high corrosion resistant, high electrical resistant, and high flexibility in structures and high dimensional stability. So these are the polymers property that is good for MEMS. I keep mentioning that for masking purpose, you use polymer. So this polymer is a kind of special polymer. We call it a photoresist polymer, are used to produce mask for creating desired pattern on substrate by photolithography technique. We will look into photolithography later on, but this is just a quick introduction to the photoresist polymer, where as for the names appear here, photoresist, so it means that it's react with a photo, with light. So with light, exposure, it will react accordingly, whether it's break the change or it join the chain of the polymer itself. The same photoresist polymer are used to produce the primer with the desirable geometry of the MEMS component in the Liga process. This process will introduce later in the micro manufacturing. Conductive polymer are used as organic substrate for MEMS and microsystem, and the ferroelectric polymers that behave like piezoelectric crystal can be used as the source of actuation in micro devices such as in micro pumping. So in one of the example later on, I will introduce a polymer for piezoelectric. So we can see that how it can behave as a piezoelectric materials as well. So particularly PVDF polymer. So the thin Langmuir blockade films can be used to produce multi-layer microstructures. So polymers with a unique characteristic are used as a coating substance to capillary tubes to facilitate effective electro-osmotic flows in microfluidic. We know that in biomedical devices, you have a microfluidic device, which is quite commonly used for identifying certain biomolecule or biomarker. So use this kind of polymer, and thin polymer films are used as electric insulator. I mentioned before in micro devices and as dielectric substance in microcapacitor. So some polymer you can have a high dielectric and some polymer low dielectric materials, then you can use accordingly. They are widely used for electromagnetic interference and radio frequency interference, shielding the microsystem. So you know that this kind of electromagnetic application and RF radio frequency application is also part of the micro device design, which people have interest. As I mentioned yesterday, is about increasing the performance of the maybe you know that RF, the radio frequency, you can have a high frequency, etc., with the low small devices. Polymers are ideal materials for encapsulation of microsensors and the packaging of other microsystems. So on top of using it in the process as insulator, etc., it can be also used as the packaging materials for the micro devices. And next is metal. Many metals and alloys are used in the fabrication of MEMS, where they serve as structural, conductive, and sacrificial layer. So this is three general applications for metals. And the choice of metal depends on the desired properties for the specific application, such as electrical conductivity, mechanical strength, and corrosion resistance. For example, we use aluminium, and we use gold, nickel, and titanium. For aluminium, a very common metals in MEMS, it is used as a structural layer, a sacrificial layer, and for electrical interconnects due to its high electrical conductivity. I think everyone aware that aluminium has a good electrical conductivity. So the deposition of aluminium on top of the MEMS surface or silicon dioxide surface, etc., is very easy. You can use even evaporation, for example, then you pattern it to make it into a circuit line. Then we have gold, valued for its excellent electrical conductivity and corrosion resistance. It is often used for electrical contacts and interconnects and wire bonding. So gold has a property which is very good when you try to connect with certain other materials, with a solder alloy, for example. So that's why if you see that your bonding pad for interconnects is you have a layer of some other metals, so for example, aluminium or chrome. Then on top of that, they deposit another layer of gold in order to make sure that the bonding is very good, or the connecting with because you want to connect your circuit with some other component as well. And nickel, known for its high strength and good mechanical properties, making it suitable for structural layers, especially in high aspect ratio process, legal process, and is often deposited using electroplating. So nickel is very hard material, hard, uh, and it's for structural design, but it's also high density. So for structural design, to use nickel quite common as well. But and I mean, because of the structural design, the deposition of nickel normally, if you want to make it into structural and higher thickness, you do electroplating. So for this, let's say gold, you use different process of deposition, let's say CVD, or you use uh, evaporation, for example. But for nickel, it's quite common to use electroplating. And titanium nitride. Titanium is strong and can be used as a structural layer. Titanium nitride offers high electrical conductivity, a large elastic modulus, and excellent resistance to biocorrosion, and making it ideal for biosensors. So next material is copper, used for electrical interconnect and structural components. Copper films are often deposited using electroplating as well. So tungsten, another material which is quite stable, used for structural application and has an extremely high melting point, and making it suitable for high temperature devices. So we can choose accordingly to what purpose of the design or the use of this material. And platinum is quite expensive, but it's a noble metal used for electrical contacts, electrode, and sensors due to its chemical inertness and excellent electrical properties. So previously, we talked about gold. Gold also an inert material, so it's same as platinum. And chromium, often used as an addition layer for another metals. For instance, a thin layer of chromium is deposited before a gold layer to improve its adhesion to the substrate. So we know certain material, we have different addition properties to different materials. So as for chromium, it has a good addition property with the silicon dioxide, silicon, and maybe the circuit board. That's why people use chromium first as a conducting layer. Then on top of that, you have your gold, for example, because gold has a good addition with the chromium. So this will provide a lasting property or the bonding pad for the materials, for the electrical circuit. And another important properties for the materials which we should consider for the device of MEMS is the residual stress. This is a critical parameters for MEMS, as tensile or compressive stress can cause structures to bend or buckle. A compressive stress in films like tungsten or titanium can be used to compensate for tensile stress in other layer. And the magnitude of residual stress is highly dependent on the deposition parameters such as temperature, pressure, and gas composition. When we deposit some materials on top of the structure of the micro devices that we try to fabricate, the process basically, if because we are depositing layer by layer. I mean, if you talk about CVD or electrode deposition, basically, if you look into electrode deposit, not deposition, evaporation, for example, when you evaporate the material and it's attached to the surface of the substrate, it's layer by layer. So basically, this development of layering thin film will cause the what we call as residual stress. So this residual stress can cause the bending, for example, the warping of the materials, the thin film. That is why we have to concern about this residual stress in our process. Then to control the residual stress, basically, you have to play around with the process parameter itself. And size effect, the mechanical and electrical properties in thin films often deviate from their bulk values. So we have discussed about this yesterday. As film thickness decrease, properties such as electrical resistivity and thermal conductivity can change due to electron scattering at grain boundaries and surfaces. So we will look into the what is meant by the electron scattering later on. And deposition method, the method used to deposit the materials such as sputtering or electroplating, and subsequent processing, if you do annealing, for example, and significantly affect the film microstructure, which in turn influence its mechanical properties, including Young modulus and residual stress. So, I mean, we have discussed about residual stress, and of course, with annealing, for example, in the bulk material processing, you do annealing also, you can change the property or improve the property of certain materials. So it's the same here. So addition, metals like gold have a poor addition to common MEMS substrate like silicon dioxide, and addition layers such as chromium or titanium is often required to ensure the film remains bonded to the substrate. So I've mentioned this before. So this is just one example. So it goes with the same concept. If you have not good addition with the substrate, you have to maybe design something with different materials or try to overcome with different concept. So, I mean, we look at a glance of properties of materials here, aluminum, gold, nickel, tungsten, etc. So this kind of properties might need to be considered before you design or decide to use certain metals or materials in your device. So accordingly, you have to look into, it's not just about the mechanical properties as well, but sometimes you can kind of have a trade-off between the property not to be high. Let's say Young modulus, you don't require at this level, but maybe you require at this level only nickel. Then you have to consider about the price, for example, and about the processing, difficulty of processing. So that is a part of the kind of consideration. And for the rest, we have silicon with I think I've shared before certain properties, but here with in comparison with silicon dioxide, for example, and aluminium, it's about the same density here, around 2 to 3.5. Then of course tungsten with higher density, and steel so with a quite high density. So you want to, I mean, in certain part, you might consider not using tungsten in your structural because it's too heavy later on. And yield strength of the materials here. And well, it's depend on whether you want to have as a structural material or you want to have a material for circuit or for insulator, etc. And okay, the comparison between silicon and steel. So you have a Young modulus of silicon 180 gigapascal, and steel 210 is not that far. And you have a almost one third density of the steel for the silicon. And thermal expansion coefficient about 1/5 of the silicon. So it's very stable in terms of thermal coefficient. I mean, it does not expand much due to temperature change. So next is when we make things into smaller device or smaller structure. So basically, you have to concern about the properties of the material. So we have discussed this, before yesterday, but this is to look into the specific property of the material. So for example, here we have silver nanoparticles. So, and with a different shape. Let's say a sphere-like particle, silver nanoparticles, you have uh, this shape, then with this kind of dimension and shape, you get different property. So when it's rod-like particles, what I mean by different property is when it's react with something, it react differently. So it might improve the reaction with certain other materials, with biomaterials, for example. So normally people try to grow, let's say, nanoparticles with different shape. You can find a lot of report in a rod shape, for example, in flower shape, nanoparticles, etc. So you can see that with different geometry, it is react differently with external material, or it provide different properties as well. And tube-like silver particle, etc., titanium dioxide nanotube. So you can see here, this is a gold nanoparticle suspended in this liquid. So you know that these are gold, but it's provide different color. So why? Because you have different size of the nanoparticle. So it absorbs different wavelength. Okay. So the absorbent property of the nanoparticle is different, then you get a different color of the nanoparticle of gold. So material properties don't change with size, uh, resistivity, melting point, and optical absorption, but the absorption property of this material change. Material properties such as optical absorption shown here change with the size of the gold nanoparticle. And I'm sorry that this is not correct. Basically, melting point at certain extent, you can get a lower melting point when you make into nanoparticle. So I'm sorry for that statement. Okay, unique characteristic of nanoparticle. When you make into nanoscale, large surface to volume ratio, we have discussed yesterday. High percentage of atom or molecules on the surface, and surface forces are very important, while bulk forces are not as important. So metal nanoparticles have unique light scattering properties and exhibit plasmon resonance. That should be okay. Figure here. Semiconductor nanoparticles may exhibit a confined energy state in their electronic band structure and can have a unique chemical and physical properties, and same size scale as many as biological structures. So why is it important here? Because you want to make it compatible with the bio device for MEMS, for example. So if the same size, is easier for it to be have a reaction. And example of unusual properties: lower phase transition temperature, increased mechanical strength, different optical properties, and altered electrical conductivity, magnetic properties, and self-purification and self-perfection. In terms of physical properties of nanoparticle are dependent on size, shape, whether it's sphere, rods, platelets, etc., and composition, and crystal structure, and surface ligand or capping, and medium, the medium in which they are dispersed in liquid, what kind of liquid. So for example here, molecules, nanoparticles, and bulk material can be distinguished by the number of atoms comprising each type of material. So here, number of atom 1 to 10 we consider as molecules, and 100 to 1 million is nanoparticles, and above than that is a bulk. So this is just an approximate number in general. And I think skip this. I think we have discussed this yesterday. I tried to skip a little bit. Okay, and for the surface area volume ratio, And you see that surface area volume ratio increase when the nanoparticle diameter decrease. So with the decrease of nanoparticle diameter, you can have a surface volume ratio increase significantly. So this, I mean, that is the reason that when we make into nanoparticle, then we can get different behavior. The ratio increase dramatically when nanoparticles diameter drops below 100 nano. And I think due to time constraint, I will skip some. Okay, if you see here, as the percentage of atom of the surface increase, the mechanical, optical, electrical, chemical, and magnetic properties change. So for example here, the silver nanoprism in this shape, you can get this different color, and silver gold nanoparticle at up to 100 nanometer, and gold nanoparticle at 50 nano up to 50 nanometer. You can see different color, and silver 120 nanometer with different color as well, and so on and so forth. With the change of the size of the nanoparticle, you can get the absorption different, then you can get different color. I think, is it time already? It's 10, right? We should continue with, I think, should I just continue this, or if we continue with different, or I can finish this slide? Lecture 4. Okay, I think I just go quickly this crystal structure, and oh, oh, a lot. Okay, but the thing is, with a different size, you can get different absorption of the material. Then you can get different properties exhibited by the nanoparticle itself. So it's about the optical properties, about the energy level, basically. Then you can have different, for example, here with a different color of emission, with different size of the nanoparticle. The 3 nano to 8 nano, you can get from blue to red of the optical properties. And some electrical properties also change due to the, let's say, this is the bulk size, and this is the nanoparticle nano size, which if we have the electron to move in free mean parts, mean free parts, I mean, and if it's too small, then free mean parts, then you can get the electron to be scattered. So this scattering of electron will somehow affect the electrical property of the material. So whether in elastic scattering or inelastic scattering, it might not change that much, almost the same. But in elastic scattering, it will change the property of the electrical conductivity. Okay, I think that's all for this session. Thank you.